Hello guys, so in the last class we had spoken about axis of symmetry. Now today we'll be talking about D and L configuration, and we'll be talking about how to find out the total number of stereoisomers for the compounds. So both of these will be covering up together. Okay, so now before we start D and L, I'll just go through a small quick revision of a thing. If you remember when we were talking about classification of stereoisomers. At that time, I told you that enantiomers can be of two types, erythro and trio, and we have never used that term ever. So I just thought, okay, let's quickly talk about these terms, that what exactly these means. If they have been asked sometime, you must know what is erythro means and what is enantiomers means and what is trio enantiomers means. So let's quickly see what are erythro enantiomers and trio enantiomers. So you look at this compound, what we have it over here. So in this compound, if you can see, we have two Fisher projections, and we have COH on the top, then hydrogen, then chlorine, hydrogen, bromine, and then COOH. Now look at the configuration here. This is 1, this is 2, and this is 3. So when you are going from 1 to 3, the rotation is anti-clockwise, and hence it is R. We have already discussed this before. Now similarly 1, 2 and 3, the rotation is clockwise and hence the configuration is S. So R and S, right? And similarly here it will be your clockwise, so it is S, and if you go from here to here it is anti-clockwise, so it is R. That's how the configuration is. Both of these molecules are individually optically active, right? If you see, you can clearly see whether there is POS or COS or not. So neither POS is there nor COS is there. So both are optically individually active. Now here, how will you decide whether this pair of, I mean, obviously these are mirror images of each other, non-superposable mirror images, and have different configurations at the chiral carbons. So now just look at this molecule. You can see the two same groups, hydrogen and hydrogen, are at the same side. So any such enantiomers where the same group is on one side of the vertical line, or same side of the vertical line, and they are optically active, are called as enantiomers. So basically for enantiomers, the definition is like that they should be optically active. So you have to check whether they're optically active or not. First of all, they're enantiomers or not, and what type of enantiomers they are. For checking that, you have to see whether their same pair of group is on the same side of the vertical line or not. When they are on the opposite directions, when these are in opposite directions, so see here, hydrogen is on the opposite direction. Here hydrogen is on the opposite direction. Both of them are optically active. Okay, then these compounds will be called as trio compounds. That's all is the classification of erythro and trio. When the same groups are on the same side, then it is erythro, and when these are on the opposite sides, these are trio. Both have to be enantiomers, both have to be optically active. Okay, so this is about erythro and trio enantiomers. Now let's go to the actual part what we were going to start, and that is D and L configuration of the molecules. So how to decide whether a compound is D or whether a compound is L. So DLN configuration. This configuration is also known as relative configuration, and this configuration is majorly used for sugars and amino acids. So basically most of the biomolecules. Okay, now when we are talking about this configuration, there are a lot of issues with this configuration, and that is the reason why it is not very widely used. And rather than that, we prefer using R and S, which is very precise and correct kind of configuration. We also call that configuration as absolute configuration. So we used to use relative configuration. Now also in many of the biomolecule compounds, you will find this configuration being used. And how to determine a configuration of a biomolecule which is an amino acid or which is your sugar, that we will learn today. But this is not exactly what we use all the time or what we prefer using. What we prefer using is R and S because it gives you the perfect picture of the molecule, and this particular configuration has some drawbacks and flaws, because of which always we may not get the right configuration of the molecule. Okay, now the first molecule or very simplest molecule on which we do this DLN configuration is glyceraldehyde. Okay, what is the formula of glyceraldehyde? CHO, CHOH, CH2OH. So basically it is polyhydroxyaldehyde. It is the smallest polyhydroxyaldehyde. But if you have a long chain polyhydroxyaldehydes or ketones, these compounds are something which are called as carbohydrates or sugars. So now look at the structure of this molecule. You will be able to see you have CHO. Okay, you have OH over here, you have OH over here. So isn't it aldehyde with multiple hydroxy groups? Exactly similar kind of structures where you have either aldehydes or ketones and then multiple OHs in the system are called as polyhydroxyaldehydes or polyhydroxyketones, and these are the ones on which we actually use this DLN configuration. Now, how do we check the D and L configuration? Let's understand. There is no complex things involved in it. It's very simple. So let's say you have this compound. I have taken the glyceraldehyde itself. So I have CHO. If I'll write the Fisher projection of it, what is the correct Fisher projection? Correct Fisher projection is that, I mean, what are the rules told by Fisher projection? That you keep in your vertical chain maximum number of carbons. Try to include as many number of carbons you can include in your vertical chain, and the carbon which is numbered as carbon 1 must be on the top. I mean, that's not a mandatory condition, but that is a perfect Fisher projection that that any molecule in a molecule, the carbon number 1 or the highest priority carbon should be on the top of the Fisher projection. So that's how exactly we have drawn the Fisher projection. We have CHO over here, we have taken it on the top, and then we have CHC in the center. This is my chiral carbon, and then we have CH2OH, and I have written it over here. Now, apart from that, we can have two ways of mentioning H and OH. Either I can write H on the left and OH on the right, or OH on the left and H on the right. Both of the projections are possible. Both of the Fisher projections are there, but both of these Fisher projections will have different configuration in terms of R and S also, and in terms of D and L also. So now if I have to check the DLN configuration, see R and S we have seen how to draw, how to write it. We just have to see the priority and accordingly we have to place R and S. Here we have to check D and L. What is the rule of checking D and L? If OH in a molecule, the molecule for which you are finding out the relative configuration, if OH is on the right side, then it is called as D, or it is referred by D, and if it is on the left side, it is referred by L. So if I have to write the name of this molecule, how will I write? I will write it as D-glyceraldehyde and L-glyceraldehyde. Okay, very simple, no complication involved. Simply you just have to see the position of OH in the Fisher projection, on which side of the horizontal line it is placed, and accordingly you will place the D and L. Now see how it happens in amino acids. In amino acids also the rule is same. If you have NH2 on right hand side, in that case the name will be D-amino acid, whereas if NH2 is on the left hand side, in that case it will be called as L-amino acid. If you remember, I had told you long back also that D represents, that was basically the small d, but you can just relate or you can remember it that way. D means the right rotation and L means the left rotation, but those were small l and small d, and this is the capital D and capital L, and these are different from each other, but still you can just remember it through that way. If it is right, then D. If it is left, then it is L. So in case of amino acid, we check the positioning of NH2. In case of sugars and carbohydrates, we check the position of OH. Now, as I mentioned that we require, see, there are multiple ways of writing Fisher projection, and there are no certain fixed rules apart from just two things, that the bonds which are coming towards the viewer should be on the horizontal line, and the bonds which are going away from the viewer should be on the vertical line. That is the mandatory condition for Fisher projection. Apart from that, to improve the Fisher projection, we have suggested many things, that maximum number of carbon should be on the vertical line, and the one carbon which is priority 1 should be on the top of the Fisher projection. All these are suggested methods to improve your Fisher projection. But when I am talking about D and L configuration, it is must to take the right Fisher projection or the perfect Fisher projection. You cannot just take the random Fisher projection. If it is randomly distributed, if any a group which is a higher priority group is on the horizontal line, do the double switch so that configuration doesn't change, but you get the Fisher projection which is the ideal Fisher projection, and then only write D and L. Do not write without rearranging the Fisher projection if it is not in the perfect manner. Okay, so let's see, we have some questions over here. We will assign D and L. It doesn't have much complications involved. Just look at it and quickly do it on your own. I have this compound, I have COH over here, I have CH3 here, hydrogen here, and OH here. Now see whether this Fisher projection is the perfect Fisher projection or not. I don't think it is. It is perfect because all the carbons are not on the vertical line. So I have to do double switch so that the configuration doesn't change. And then I'll make a new Fisher projection and then I will assign D and L. Otherwise, the configuration will also be wrong. So what we have done, we have switched the position of CH3 and hydrogen and then CH3 and OH and eventually got this as a molecule, right? This is the lactic acid molecule. And now I can see my OH is on the right. So the name of this compound is D-lactic acid. Now next, look at this molecule. First of all, let's convert it to the Fisher projection. So I have COH over here, CH3 over here, hydrogen here, OH here. No need to make any change because it is already in the perfect form. Because OH is on the right, the configuration is D. Look at COH. This is hydrogen. COH, hydrogen, NH2, my bad, it is typo, please correct it, NH2 and CH3. So NH2, already this Fisher projection is in the perfect manner. NH2 is on the right, so the configuration is D. If I have multiple chiral centers, there also we will be individually assigning D and L. So if you look at the next example, I have CHO, then hydrogen and OH on the second carbon, OH and hydrogen on the third carbon, and hydrogen and OH on the fourth carbon, and CH2OH. The chain is already in the perfect position, or you can say the Fisher projection is already in the perfect structure. Now we just have to find D and L individually for these carbons. For the second carbon, the configuration is D because OH is on left, so I will write 2D, comma, the third one is L, so it is 3L, and the fourth one is also D, so hence it is 4D. So this is the configuration, whatever the name of this molecule would be, that we will be writing, and this is the configuration for those chiral carbons where you have OH and hydrogens placed. Okay, so now look at the fifth one. Fifth one has NH2 and OH, both the groups present here. And we have CH3, CH2. Fisher projection looks okay. If you see over here, NH2 is on right and OH is also on right, but still I have written it as L and L. Why? Why? Because we always want the higher priority groups to be on the top. Though here CH3s, we cannot say which one is higher priority, which one is lower priority. Both of them are same. But the next higher priority group is the OH, which is on the second carbon, which should be on the second carbon. But it is, according to this Fisher projection, it is coming on the third carbon if I count it from here. So we can do two things. One is we can either start the numbering from here, 1, 2, 3, and 4, or I can rotate the molecule. And if I'll rotate the molecule, then what will happen? Then this molecule will become this. It will be OH here, NH2 here, CH3 here, CH3 here, hydrogen here, and hydrogen here. So rotation I will do to bring the higher priority group above and the lower priority group down. We all know that OH is higher priority group. Now we will assign the D and L to it. Now both of the OH and NH2s are on the left, and hence the configuration is L. I hope you have understood what I have done over here. So a higher priority group, I want to bring it up. Either I can start counting from the bottom and then check it accordingly, or better way is you rotate the molecule and then bring the OH and NH2 at the right places so that the higher priority group is on the top, or as higher as possible, and then we will write the D and L configuration for these molecules. Okay. Now look at a few more compounds. In next compound, we are talking about the glucose and fructose and so on. So basically, if you talk about glucose, glucose is also a sugar. And if you see the structure of the glucose, this is polyhydroxyaldehyde. Okay, this is our polyhydroxyaldehyde. In this, we will individually mark the chiral carbons, and then we will start finding out the DLN configuration. So OH is on the right, so the configuration with this is D, and this is L, then this is D, and this is D. So this is the configuration. If I have to write the name of my glucose, then it will be 2D, 3L, 4D, and 5D. Apart from that, how many OHs are there? Total 5 OH are there. All the OH are lower priority groups, so pentahydroxy. And because there are 6 carbons in total, hexanal. This is the name of the glucose. And this glucose, in short, will be written as D-glucose. Why it will be called as D-glucose? Or if you talk about its trivial name is D-glucose. Why it is called as D-glucose, though it has D and L both kind of configurations? We always look for the farthest chiral carbons configuration. So this is my carbon 1. right? And the farthest chiral carbon is here on the fifth position. What is the configuration for it? D is the configuration for it. That is the reason the name of my glucose will be D glucose. So we will always be looking for the farthest chiral carbon's configuration, and that will be the term, or that configuration will be assigned to the name of the compound. Similarly, if you look at the glucose, the other isomer of the glucose, or you can say the other enantiomer of the glucose, then it has CHO here, OH here, so it is L, it is D, it is L, and this is L. This is the mirror image and enantiomer of the other glucose. So name will be 2L, 3D, 4L, 5L, 2, 3, 4, 5, 6 pentahydroxyhexanal, and the name will be L-glucose because the farthest chiral carbon is L. Okay, so this is how we figure out the configuration for glucose. Now let's talk about the fructose also. So fructose, this is the molecule of fructose. So here it is, rather than being a polyhydroxyaldehyde, this is polyhydroxyketone. So here this is my ketone, which is on the second position. I cannot place it at the first position because it is ketone. Okay, but this is the higher priority group, and hence we have to keep it on the top. Now you see the chiral carbons are just 3. There are not 4 chiral carbons like your glucose. So here the if I write the configuration here, this is L, then this is D, and then this is D. The farthest chiral carbon is this one, right? And what is the configuration for this? D. So the name of this fructose will be D fructose, and if I have to write the name of this whole molecule, that is IUPAC name, because this is D-fructose is a trivial name. Okay, if I have to write the IUPAC name, then it will be 3L because this is the third carbon, 4D, 5D, 1, 3, 4, 5, 6 pentahydroxyhexane 2-one. This is the name of fructose. Okay, you need to know these structures, you need to know these names very well, not only for this but also for biomolecules chapter, which you will be doing in class 12th portions, and that will be important. I mean, that's the fructose structure, glucose structure, and the D-glucose structure, L-glucose structures. All these are very important part of your biomolecules chapter. Now what you have to try on your own is, I have told you what is the structure of D-fructose. Draw L-fructose on your own. What next we will start? We will start how to find out the number of stereoisomers, which include your optical isomers and which include your geometrical isomers. So next part is number of stereoisomers, how to calculate the number of stereoisomers if a compound is given. So as I had earlier mentioned, that number of stereoisomers include your optical isomers and your geometrical isomers. So there were some formulas which we had done in optical isomerism also, and in this also we have the formula, and you will find the similarity in the formulas also. But as the thing I explained you in the case of geometrical isomerism, that maximum try to visualize and then try to figure out the isomers on your own rather than relying on the formula. Relying on the formula is not right, and many a times you will find in the compounds where formulas are not work. It is always suggested that you try to find out the isomers on your own, and then if the compound is very lengthy or anything like that, use formula. But it is always a better practice to try out finding out the isomers on your own. Even though when I'll be giving you the formula, when I'll do the questions, I will show you what exactly isomers are forming to just cross check. So it becomes a double effort that you use the formula, get some value, then cross check. Rather than that, it's better always draw the isomers on your own and then count them. Okay, so there are two cases exactly same way how we had in the case of optical isomers. If we have a compound and it has dissimilar ends, then the number of stereoisomers is 2 raised to power n, where n is the number of stereocenters. So when I say stereocenter, it is chiral center as well as the stereocenter, which shows the geometrical isomerism. So basically, if you remember, we had done the stereocenters in case of GI also. So we will be including a GI stereocenter also, and I will be using a chiral center from the optical isomers also. Okay, so basically chiral center in terms of stereo, in terms of optical isomerism, and GI center in terms of GI isomerism. Okay, now if the compounds have dissimilar ends, then there can be two cases. One is n is even, another is n is odd. When n is even, then the formula will be 2n minus 1 plus 2n by 2 minus 1. So this is a little different formula. This formula is same as what we had done in the optical. So here 2n minus 1 represents the optically active isomers, okay, and 2n by 2 minus 1 represents the meso compound. So here you get the count of meso and optical isomerism separately also. So you can actually separately count if somebody asks you how many meso isomers are there or meso stereoisomers are there. So you can actually see using this formula. But that is only in the case of even. In case of odd, you may not be able to find it. Mostly your mesos are in the are only in the even ones. In odd ones, generally there are not much mesos, but there are cases where you may find the meso compounds in n is equal to odd also. So in that case, this formula will not give you the exact number for mesos. Okay, so here it is giving you just a total number of stereoisomers. Now let's try applying these formulas to our questions. First compound what I have is CH3, CH with fluorine, chlorine and CH3. So just see whether it's a dissimilar ends or the similar ends. This is a dissimilar end. So if I use the formula, I'll get 2 raised to power n, that is 2 raised to power 2. Two chiral centers are there, one is here, one is here. And the number of isomers which you are getting are 4. Let's cross verify, are we actually getting 4 or not? So first of all, if I'll draw the Fisher projection, that's how the Fisher projection is going to be. H and F, H and Cl, and then I can have I mean you can just do the variation in the same F and H, H and Cl, CH3, then again CH3 and H here, F here, Cl here, and then the other variation is Cl here, hydrogen here, H here and F here. So now if I'll try to find out the RNS configuration for this molecule is for this center is this is 1, this is lower one is 2 and this is 3. So if I'll go from 1 to 3 it is clockwise and it is S, and the down one is like this, so it is anti-clockwise and it is R, so SR. I have written it here, different combinations or different you can say different isomers what we'll get. So one isomer is SR. Here in this case the rotation is going to be this, that is anti-clockwise, so this is going to be R. And if I go for this, again it is going to be anti-clockwise and this is going to be R, so RR, right? Now look at this, this is going to be clockwise, so this is S, this is going to be anti-clockwise, so this is R. Did I draw the same thing? Yeah, I have drawn the same thing, my bad. So it will be, the other isomer will be fluorine here, chlorine here, hydrogen here, CH3 here and CH3 here. In this case, this will be R going like this will be R, and if I'll go like this it will be S, so RS. Okay, and you look at it, this is gonna be S and S, so this is this. These are the 4 isomers what we have got, and we cannot get anything apart from that. Okay, so this is just a confirmation. It's preferably draw this way and then confirm with the formula. So this is how it should be done. Whenever you are getting a compound and you are using the formula, it is important and required to cross check what all isomers you are getting, because not always it will be matching with the formula. Look at the next compound. What is next compound here? I have CH3, CHCl, CH double bond, CH3. So I have 2 chiral centers here. One is the one is this, and second is this, which can show GI. So I told you N is the number of stereocenters, and stereocenter will include the stereocenter of the normal carbon chain, basically sp3 carbon, as well as the carbons which can show GI. Okay. So there's similar ends and the formula is 2 raised to power n. So 2 raised to power 2. So answer is 4. Let's confirm whether we can have this or not. I'm not going to draw the structure. You draw it on your own in the notebook. I'm just going to tell you what all different combinations you will be getting. So this particular carbon can become R and S. On this particular stereocenter, what variation we can get? Cis and trans. So we just have to draw the combinations of this. So R with cis, R with trans, S with cis and S with trans. So these are the 4 structures which can be formed. Now look at the question number 3. In question number 3, if you see, it has the similar ends. Especially in the case of similar ends, you will find there would be many cases where there will be meso compounds forming. Okay, so here you have to be a little careful, and it is required to draw the structures. So if I use the formula, I will get 2 raised to power n minus 1 plus 2 raised to power n by 2 minus 1. Two chiral centers are there. You'll apply the formula. Answer you'll get is 3. Two are optically active compounds and one is meso. So let's confirm whether it is right or wrong. Let's draw it. So what all different things can be drawn? CH3, OH, H, OH, H, and CH3. This is one possibility. Okay, we will draw all the possible structures and then we will find out the configuration for them. Then there is HH here, OH, OH here, and then CH3. Then other possibility is you draw it as CH3, OH, H, HOH, and CH3. And the fourth possibility is you draw it as CH3HOH, OH, H, and CH3. Now just look at the configuration here. It will be OH, CH, H, and CH, OH. Then second is a lower molecule, then CH3. So this kind of this is anti clockwise. So this is gonna be R, and similarly this is gonna be S. Okay, this is clockwise and this is S. Exactly same way, look at it. So this is gonna be S and this is gonna be R. So this is RS, this is SR, but look at the molecule very carefully. Does it possess POS? Look at the center. Yes, this possesses the POS. So these are identical. The first compound and the second compound are identical and meso. So we can't consider them two different compounds, but we will have to consider only one single compound, because these are identical and these are optically inactive and they have plane of symmetry. So you can rotate and you get the same molecule, right? So these are your meso compounds. I mean, there is just one meso compound. Okay, this is one. These two are identical, absolutely identical compounds. Okay, so this is one meso. So you can't consider RS and SR as are two different things. These are same. No matter you write it RS or you write it RSR. Okay, so one is meso. What about these? This will be OH to CH3. So this is what? This is anti-clockwise. So this is R. Okay, and OH, this is again anti-clockwise, so this is R. Okay, exactly same way, this will be S and this will be S. Now these are individually optically active, no POS, and they are mirror images of each other. So these two compounds are enantiomers of each other. So what all possibilities are there? RR, SS, these two are going to be enantiomers of each other and optically active, whereas RS and SR are both same and meso. Okay, so this is how you're gonna find it. So just see wherever the similar ends are, there will be meso compounds. Most of the time there will be meso compounds, and you have to be very, very careful about it. Many a times the formula itself will cover it, and many a times you may just get tricked. Okay, so you try out solving it on your own by writing the compounds. Okay, so now let's talk about this fourth question. In this fourth question, what we have is we have CH3, CHBr, 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 CH3. So there are two chiral centers. One is this one and one is this two. This carbon is not acting as a chiral center. Why? Because the same groups are present here and here, right? So even number of chiral centers and similar ends. So what will be the formula? 2 raised to power n minus 1 plus 2 raised to power n by 2 minus 1. So formula will be 2 raised to power 2 minus 1 plus 2 raised to power 2 by 2 minus 1. So it comes out to be 3. Now I'll explain you how exactly there are three compounds, and here you have to check, and then we will learn a very small important thing also. So if I draw the structures, these could be the structures of the molecules. I have drawn four possibilities over here. Here this carbon is not chiral. This is R, this is R. So we can write the configuration as 2R, 3 achiral, and 4R. Okay, now is this optically active? Yes, it will be optically active because there is no POS and no COS, right? No POS, no COS, optically active. Yes, it is optically active. Now let's talk about this. CH3, exactly same case is here, and it is the mirror image of this. So 2s, 3 achiral, and 4s. Now look at the next one. So in this case, it clearly looks like meso. I told you what exactly is the meso is, that you cut the line through the center, and then if you get the two equal halves. Apart from that, but I want to tell you one more thing. So if you look at this, the configuration for the second carbon is S, and the configuration for the fourth carbon is R. So configurations differ, but if you pass a line through the center line is acting as a plane to cut into two equal halves. So this is meso and this is meso. So basically, if you look at this molecule, it is also exactly same. This is R and this is S. No optical activity, and this is also meso. So basically, these two are going to be identical compounds, right? You rotate this molecule and you'll get exactly same thing. But you look at this third carbon, what is here? Third carbon, which was looking like it is non-chiral or it is a chiral, is actually chiral over here. It's not actually chiral. We call it as a pseudo-chiral. And why it is being called a pseudo-chiral? Because it is not chiral due to the presence of two different groups. It is chiral because of the presence of two same groups but having different configuration. Such kind of carbons are called as pseudocarbons. So we have pseudo-chiral carbons. Okay, so we don't, and they're not included in the chiral centers. So I'm just telling you that this third carbon is acting as a chiral carbon just because it has two different configurations. The molecule is same, but the configuration is different, and hence such carbons are called as pseudo-chiral carbons. What is the definition of pseudo-chiral carbon? The carbon which is chiral just because of the difference between two individual groups present at the difference between, not I think I have I have done a small mistake over here. Just correct it. Difference in the configuration of two same groups present at the center. So this is the definition of pseudo-chiral carbon. Okay. Now let's talk about the next set of questions. So next question is, I have CHOH, CH double bond, CH, CHOH. I have three chiral centers over here. One is here, one is here, one is here. Or stereo center, you can say, not chiral center. So this is one which will show GI and this one will show chiral behavior. Or you can say they are chiral because four different groups are present over here. Now according to formula, what formula should it be using? 2 raised to power n minus 1. So 2 raised to power 3 minus 1. So it is equal to 4 because the dissimilar ends are there and the number of stereo centers are odd. So this is going to be the formula, 2 raised to power n minus 1. So now let's see whether it's actually right or not. So what all is possible on this carbon? R and S configuration possible here, R and S configuration is possible over here, and cis and trans is possible here. So basically whatever combinations will form from these three. So let's quickly check. It will be R cis R, okay. Then it can be S cis S. So basically the configuration changing on these two carbons, whereas the cis is remaining cis. R trans R, S trans S, R cis S, and S trans S. Okay, so these are the 6 possibilities over here. So these are the 6 possible structures which can be formed, but the formula says 4. So here is the example where your formula can be wrong and you have to actually go and check whether it is giving you same number of stereoisomers or not. Okay, so look at the next compound. Next compound, what we have is 2 benzene rings, and those both are in a different plane. Their groups are in different plane. No POS, no COS. So this whole system itself will act as a chiral center. And there is one more chiral center over here, which is here in this chain. So if you see this chain has this carbon present over here. This carbon which is acting as a chiral center. So there are 2 chiral centers or 2 stereo centers, you can say. So the formula will be 2 raised to power n, 2 square, or 4. Now here again there will be 2 isomers formed because of the whole system here. Okay, we don't know how to figure out this. I mean, we have not done it till that detail or depth that what exactly these isomers will be called as. Whatever the optical isomers are going to form from this dibenzene kind of ring structure. Okay, and then one set of isomers will form over here, that will be RNS. And assume this whole benzene setup itself also forms RNS, then the combination will be R, 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 S, 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 and S, R. So 4 possibilities are there. Okay, so this is how exactly we figure out the chiral centers. Now in such kind of examples where you exactly don't know how dibenzene thing shows the optical activity and what those optical isomers are called as, here you can use these formulas and you can get the exact numbers. Look at the next example. Next example is this. We have C, CHCl, CH3. So basically 4 such groups are present on this carbon. If I open the structure will be like this. Cl hydrogen CH3, Cl hydrogen CH3, Cl hydrogen CH3, Cl hydrogen CH3. So I have put 4 Fisher projections on the center carbon. So center carbon is not chiral, but individually each of these carbons are chiral, which have been represented by cross. Right? Now, when these have been represented by cross, so these are 4 chiral carbons, so 4 stereocenters, and individually they can show R and S configuration both. So what all different possible isomers are there? I can have all the 4 as RRRR, then I can have 3R1S, then 2R2S, then 1R3S, then all the 4 as S configuration, and the combination of R, S, R and S. Okay, so here we number of isomers we have got is 6, and by any formula you're not gonna get this as an answer. So here for this molecule no formula works. It is all your own visualization and the method how to determine the different isomers. That skill is required to get the right number of isomers. So there will be most of the cases what you'll be getting in the competition exam like mains and advanced will be majorly based on such kind of questions where you will have to reconfirm it through your visualization also, and you just cannot rely on the formula. So be careful while marking the number of stereoisomers, total number of stereoisomers. Okay, so here we are done with the today's thing, that is we have done D and L configuration, and we have spoken about the how to find out the number of stereoisomers in a compound. Practice and practice more so that you get to know what kind of mistakes can happen in the actual exam, because you may know the fundas, but unless you experience or you encounter different kind of questions, you won't know how to apply those fundas to solve the question. In next class, we'll be talking about racemic mixture, polarimeter, and we will find out how to calculate the percentage purity, and there are many other things which we'll be covering up. Next class is going to be mostly the last class for optical isomerism, and we will be done with this part, and we will be moving to the third topic of this isomerism, and that is your conformational isomers. Okay, till then watch it, solve questions. It will help you and you will get a better clarity on whatever you have learned till now.